So the first problem asked how high it'll go, and it got copied a little funny, but you can still read it. So if you're thinking how high it'll go, you need to think vertical, because the height is vertical, not horizontal. So it was told that the soccer ball was kicked at an angle of 40 degrees above the horizontal with a velocity of 20 meters per second. So it's not telling me the vertical or the horizontal, it's telling me my hypotenuse. So this vector here was 20 meters per second. So this vector is part horizontal, part vertical. And if I want to know how high it'll go, I want to just know the vertical velocity. I don't care anything about the horizontal part. I just need to know something about the vertical velocity. So I can use my trig functions to solve for the vertical velocity by using sine opposite over hypotenuse. So once I do that, I know the vertical velocity is 13 meters per second. So I can write that in here, 13 meters per second. And we know as it goes up, my acceleration is always going to be 9.81. So again, when I make that column, my x and my y column, all this information over here would be written down over here. So I know that the acceleration is the whole time is going to be negative 9.81 because it's going to go up, slow down, and then speed up as it comes back down. So the whole time the acceleration is negative 9.81. And then right here, as it's kicked, that velocity right there is 13. And over here, right before it hits the ground, that velocity is going to be negative 13. And we also know at the highest point, that velocity is going to be 0. So we can say that the velocity at the maximum height, or we can say at the peak, is 0, which is this point. And then the initial velocity right here, as it goes up, is positive 13, and the acceleration the whole time is negative 9.81. And again, it's slowing down as it makes its way up, so we have to have opposite signs for my acceleration and my initial velocity. So we're solving for delta x. The only other variable I don't know is time, so there's only one equation I can use if I don't have time, which is vf squared equals v naught squared plus 2a delta x. So when I plug the variables in over here into this equation, I get a displacement of 8.61 meters. So as it's kicked, it's going to go a height of 8.61 meters above the ground. So the next question asks, how much time does it spend in the air? And again, you need to think vertical, because in your xt, xy column, again, we have x, v, t here. We have no information over here that we know. We could solve for this velocity by using cosine of the triangle that we did on the last slide, but we still, in order for us to solve for time, we would have to know how far horizontally it goes, and we don't know that. We do have a lot of information over here in the y column. All this information we know is over here in our y column. So it's better for us to think vertical when it's asked how much time does it spend in the air. So I know, again, at the maximum height, that velocity at the maximum height is 0. The initial velocity as it's kicked up is 13. The acceleration the whole time is negative 9.81, and we just solved for on the last slide that it goes up 8.6 meters above the ground. So at the maximum height, it's 8.6 meters above the ground. So we want to solve for time. So really, again, there's always more than one way that you could solve the problem. Over here, we could solve for how long it takes to make its way up to that halfway point, and then double it, and we know that it will takes that exact same amount of time to go back down. So if we solve for the amount of time it takes just to go halfway up, we can say that the final velocity at the maximum height is 0. The initial velocity as it makes its way up vertically is 13. The whole time my acceleration is negative 9.81. So to go from this point to this point, it takes 1.325 seconds. So 1.325 seconds here, and another 1.325 seconds here. So doubling that, the whole time it takes me 2.65 seconds. Another way you could think about it is here. We know like I showed on your last slide, this velocity here is the same as that velocity there. So this was positive 13, this was negative 13 right before it hits the ground. So we could think about it going from this point to this point. So we know the velocity right before it hits the ground is negative 13. The velocity right here is a positive 13. The whole time your acceleration is negative 9.81 because it slows down and then speeds up. And again, you're going to get the exact same answer. So either how, it doesn't matter how you think about it, you're going to get the exact same answer. Now there is another way to solve it, which is probably the least favorite method, but you can also use the quadratic formula to solve it, because if you use our delta x equals 1/2 at squared plus b naught t and plug our information in, we know as it goes up and comes back down, it's this point right here, right before it left the ground, should be the exact same distance right here. So if this is 13 and this is negative 13, they're the exact same distance off the ground. And if you start here and you end here, that displacement is 0 because you go up and then you come back down at the exact same spot. So your vertical displacement at this point to this point is 0. So here we use that, think of it that your vertical displacement is 0, 1/2 at squared, and we're solving for t. We know that initial velocity over here is 13, positive 13, because again, if from here to here, we're looking at the whole motion from start to finish, that vertical velocity, displacement, is 0. So you have to go back to the beginning when you're talking about your vertical velocity, and then plug that numbers in, use the quadratic formula, and again, you're going to get the exact same answer, 2.65. So either use one of the methods from the previous slide, or you can use this with the quadratic formula. So here are the two columns. So here's a lot of the information that we figured out. We knew this. We calculated this by using my trig, functions, and then we knew this because it's the velocity right before it's the ground, which is the same as the initial velocity as it left the ground. The acceleration the whole time is negative 9.81. We calculated the maximum height off the ground. The total displacement from start to finish vertically is 0, and the whole time it takes from start to finish was 2.65 seconds. So when we talked about the projectile notes before, when I dropped an object and I launched something horizontally, they hit the ground at the exact same time. So the time it takes to fall vertically is the exact same time it takes for the horizontal motion. So if you know the time horizontally, you also know the time vertically, or vice versa. Because again, if you drop something and launch something horizontally from the exact same height and release it at the exact same time, they're both going to hit the ground at the exact same time because they're both projectiles and they're both falling at the exact same rate, 9.81 meters per second. So every single second it's going to go down. One's just going straight down, one's going horizontal at a constant horizontal velocity, but the vertical velocity is changing at the exact same rate. So here's our information that we know so far. So the next problem wants to know how far away from you when you kick the ball will it hit the ground. So it's asking for the range. So you kick the ball from here, goes up. It's asking how far away from you. So it wants to know the horizontal displacement. So we're just going to use our trig functions. So we were told it was kicked at an angle 40 degrees above the ground at a velocity of 20 meters per second. And again, that 20 meters per second is part horizontal, part vertical. I don't care about the vertical part for this part, so I just want to know horizontally of this 20 meters per second, what is that? How much of that is just the horizontal motion? So I'm going to use, again, my trig functions to solve for that. So this is adjacent over hypotenuse. Plug it in my calculator in degree mode, and I get a velocity, horizontal velocity of 15.3. And again, we knew that this was 13 from before. So again, in your column, you only have 3 variables because the whole time as it makes its way up and over, that horizontal velocity is constant the whole time. It's not changing because there's no force pushing or pulling on it horizontally, so it's constant. So we have to use our one equation for constant velocity. So in my xt column, xy column, we're solving for x. We just solved that the velocity was 15.3. We know that the time vertically and horizontally is the exact same, which was 2.65. So now I can solve for the horizontal displacement by plugging it into this equation and solving for it, and then you get a horizontal displacement of 40.5 meters. So the next question we already talked about in past slides. It says, what is the ball's velocity when it hits the ground? So here we have our diagram. We knew right here that this velocity vertically was 13. And we already talked about this velocity right before it hits the ground was negative 13. So you can think about it that, or if you're thinking about the vertical motion, we also know that it was launched right here, 20 meters per second. So if it's coming back down, you could also say that that velocity is negative 20 meters per second. Or if you're thinking about it horizontally, again, the horizontal velocity is not changing the whole time because there's no forces acting on it. As it makes its way up, there's nothing pushing or pulling on it left or right the whole time, so that horizontal velocity stays constant the whole time. So the ball's velocity when it hits the ground is exactly the same as it was when it was originally launched, 20 meters per second at 40 degrees up from the horizontal. The only difference is that now it's spiking the ground going down and not up. These are some helpful hints that I told you way back when we started our acceleration units. So the sign of the delta x, again, is going to help you determine the direction, if you're saying up is positive or down is negative. If an object is just going down, falling, that means it's speeding up the whole time. You're going to make all three variables, your delta x, your acceleration, and your velocity, all positive or all negative. If the object is going up and then coming back down, that means it's going to be slowing down and then speeding up. So if you think about the finger dance, your velocity and your acceleration have to be opposite. So either the velocity is positive, if you're saying up is positive, then you'd make your acceleration negative, and as it goes up and then it comes back down, you'd make your displacement negative also. And that's kind of only if it's being launched off an elevation going up like this and it's falling below down here from where it started. You'd make the displacement. If it's not being launched off of something elevation, obviously the vertical displacement would be 0. So this is pretty cool. Now I say that you now have enough information to do this. So if you click on this first link right here, it shows a guy going down a pretty awesome water slide. And the Mythbusters saw that YouTube and wanted to see if it was true, and they tested it out themselves. It's not the whole video